So the other day, I'm in the garage, right? And I'm staring at this hopeless, just twisted pile of 3 extension cords.
Oh, no, I know exactly what you mean.
Right. And I tug on one, fully expecting to just make the knot worse. But miraculously, the whole mess just falls apart. Pulling that single cord completely untangled the other two.
That is incredibly satisfying when that happens.
It really is. And, it actually got me thinking about you, the listener, and the actual mathematical version of that exact scenario. Because that's our mission for you on today's deep dive, exploring the Borromean rings.
Yeah, it's an incredibly elegant concept, honestly.
Yeah.
Like, if you picture 3 closed curves that are linked together, but here's the catch with it. No 2 are actually linked to each other.
Wait, no 2 are linked.
Exactly, no 2. Yet together, all 3 are inextricably bound. So
Yeah.
if you cut or, remove just one, the other 2 instantly fall completely free.
Okay, so it's sort of like those interlocking metal puzzle rings, where if you look closely, ring A isn't actually hooked through ring B at all.
Right, exactly.
But because ring C weaves over and under both of them in a very specific way, the entire structure locks. And then you remove C, and A and B I guess they just slide apart and fall onto the table.
You nailed it. But what's really fascinating is the sheer geometry required to pull that off.
Yeah.
Because if you try to build Borromean rings using 3 perfectly flat, rigid circles in 3-dimensional space, it is actually mathematically impossible.
Oh, really? Why is that?
Well, planes just collide. To make it work in physical space, you actually have to warp them, like bending them into ellipses or wobbly curves.
Okay, that makes sense. But is this just a quirky, abstract puzzle for topologists, or does the universe actually use this blueprint in physical reality?
Well, it absolutely builds things this way,
Right.
all the way down to the quantum level.
Oh, way.
Yeah, so back in 1970, a physicist named Vitaly Efimov predicted a state of matter, which is now called the Efimov state. And he theorized that 3 particles could bind together, even when the attraction between any 2 of them is far too weak to form a pair.
Wait, back up. So if atom A and atom B essentially ignore each other, and A and C ignore each other, how does tossing atom C into the mix suddenly act like quantum superglue?
Right, it completely defies common sense at first.
It's like the ultimate atomic 3 musketeers, all for one and one for all.
That is a great way to put it. And it makes sense when you realize that in quantum mechanics, particles act like waves. So imagine 2 very faint ripples in a pond passing through each other.
Okay, so nothing really happens.
Exactly, nothing happens. But at a third ripple at exactly the right spot, and their waves overlap and amplify each other, creating a perfectly stable standing wave.
Oh, wow.
Yeah, they bind together purely because of that 3-way geometry. It's not even a chemical bond, it's a topological one. We actually finally proved this in a lab in 2006 using ultra-cold cesium atoms.
That is absolutely wild to wrap my head around.
And it actually gets better. These states exhibit what's called discrete scale invariance.
Discrete scale invariance, what does that mean for us?
Well, imagine finding one of these 3 atom clusters. If you zoom out exactly 22.7 times, you'll find another stable, identical cluster. And if you zoom out 22.7 times again, there's another one.
Wait, just infinitely?
Yep. It's an infinite series of Russian nesting dolls made of quantum ripples, basically scaling up by that exact mathematical factor.
Using complex, invisible patterns to solve seemingly impossible problems actually reminds me of what we try to do with artificial intelligence.
Oh, for sure.
Which is actually a perfect time to mention Embersilk, who sponsored our deep dive today.
Yeah.
If you're trying to figure out where AI agents or automation, software development, or integration can make the most impact in your own business or personal life, they are the absolute experts at untangling those systems.
They really are.
Yeah, so you can check out embersilk.com for your AI needs. But anyway, back to these quantum Russian nesting dolls.
Right. Well, just like AI is optimizing our complex systems, these Borromean structures are actually optimizing our technological future. Specifically, they're paving the way for topological quantum computing.
Okay, break that down for me. How does a math puzzle from my garage help build a quantum computer?
Well, normal quantum computers are highly fragile, right? Like a stray change in temperature or some magnetic interference can easily destroy the data.
Ah, right, the decoherence problem.
Exactly. So enter theoretical particles called non-Abelian anyons. And what makes them special is that they actually remember their past paths. When you move these particles around each other through time, their paths form braids.
Oh, like weaving threads together.
Exactly. And by using Brownian braids, which are essentially Brownian rings stretched out through space-time, we can protect that delicate quantum information.
Because the information is in the braid itself.
Yes, the information isn't stored in any single particle, it's stored in the knot itself. And you can't untie a knot just by wiggling one piece of the string.
That makes so much sense. So local errors or noise just can't destroy the global structure.
Exactly. We are literally using the math of unbreakable unity to engineer flawless quantum computers.
That is an incredibly optimistic horizon. I mean, it just shows how capable we are at engineering solutions to our greatest challenges.
It really does. And it raises a beautiful realization for you to think about, too. The Borromean rings started out as a simple medieval heraldry symbol, like a family crest.
Oh, I didn't know that.
Yeah, yet that pure imagination perfectly predicted the quantum binding of the universe and our incredible future of computation. It just proves that human imagination so often intuitively grasps the physical universe before we even discover it.
So the next time you're frustrated by a tangled mess of chords, remember that the universe is actually built on those beautiful, impossible knots. And pulling the right thread might just unlock the future.
I love that.
If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out to curious minds like yours. Thanks for tuning in.